In this video, we explain what gas oscillating high temperature melt pump, abbreviated as GOHM-PUMP, is, the background to its development, its expected applications and market size. What are the nuclear fusion reactor, sodium-cooled fast reactor, solar thermal storage power generation, and molten salt reactor shown in the slide all have in common? You might hear the answer that they are carbon-free power generation systems. That is absolutely correct, but they also have something else in common. These four power generation systems are devices that use high-temperature liquids such as molten salt or liquid metal, in other words, high-temperature melt, to extract heat and rotate turbines and generators to produce electrical energy. The high-temperature melt is circulated between the heat source and the heat exchanger by a special pump. This special pump is the high-temperature melt pump, the subject of this video. The high-temperature melt pumps shown in the slide are the sodium-cooled fast reactor MONJU constructed in Japan and the molten salt reactor MSRE. The MSRE is a molten salt experimental reactor constructed about 50 years ago at the Oak Ridge National Laboratory in the United States and operated without accidents for 4 years from 1965. Both are centrifugal pumps that rotate an impeller and transport liquid by centrifugal force. Most of the pumps for sodium-cooled fast reactors and molten salt reactors developed around the world use this type of pump. Centrifugal pumps require bearings to support the pump shaft that rotates the impeller. The upper bearing of the sodium pump in MONJU and the two upper and lower bearings in the MSRE use ball bearings. Lubricating oil is required for the ball bearings to function smoothly. High-temperature melt pumps generally have to transport high-temperature liquids of over 500 degrees Celsius, but since the flash point of lubricating oil is around 300 degrees Celsius, pumps that handle high-temperature melt of over 500 degrees Celsius are required to cool the lubricating oil. In MONJU, the pump shaft is extended to about 10 meters to suppress heat conduction and reduce the temperature near the bearing, while in MSRE, the lubricating oil also functions as a coolant for the bearings. To solve this problem, due to these efforts, the pump structure must be extremely complex. Maintenance work involving removing the pump shaft should be carried out after the high-temperature melt discharging and being cooled down. However, the high-temperature melt after cooling solidifies creates a troublesome problem in that the pump shaft is prone to sticking to the surrounding area. Removing the pump shaft for maintenance is difficult work. Furthermore, in high-temperature melt pumps used in nuclear reactors, leakage of the cover gas filled in the pump is absolutely unacceptable. However, centrifugal pumps are structurally destined to have a shaft seal in most cases, and the shaft seal is required to have the contradictory functions of allowing the pump shaft to rotate while sealing in the cover gas of the high-temperature melt. While trying to come up with creative solutions to these issues, the individual design requirements of each high-temperature melt pump must be met, making the pump structure increasingly complex, requiring large costs and long development periods. In addition, since the maintenance problem is the most difficult to solve, in order to put these reactors into practical use in the future, pump designs with a completely different concept from conventional ones will be required. Let's go back to the origin of pumps and consider them. Pumps, which are devices that transport liquids, are broadly classified into turbo pumps, which include centrifugal pumps, and positive displacement pumps, which include piston pumps. Turbo pumps mainly use the centrifugal force generated by the rotation of an impeller to provide energy to liquids. On the other hand, positive displacement pumps provide pressure energy to liquids by compressing them by reducing the volume of space. There are two types of pumps: reciprocating pumps, which use reciprocating motion, and rotary pumps, which use rotary motion. As explained in the previous slide, the issues with conventional high-temperature melt pumps arise due to the presence of bearings on the pump shaft, so it seems that positive displacement pumps may provide a clue to solving the issues. However, since rotary pumps still require bearings and shaft seals to rotate gears, let's consider reciprocating pumps. Typical reciprocating pumps are piston pumps, plunger pumps, and diaphragm pumps. These reciprocating pumps are similar in principle. Difference is whether the tool that gives the reciprocating vibration energy to the liquid is a piston, a plunger, or a membrane called a diaphragm. The combination of a double diaphragm pump and a check valve allows for continuous liquid pumping, and is often used in industrial applications. There is no material other than metal that can be used as a diaphragm for high temperature melts above 500 degrees Celsius, but a metal diaphragm may break at a metal fatigue after long-term use, and it is considered difficult to use it for a high temperature melt pump. So we will proceed with the study of a reciprocating pump other than a diaphragm. As shown in the conceptual diagram on the right, you can see that the fluid circuit functions as a pump by converting the vibrations of the liquid into direct current through a check valve that functions as a diode, similar to an AC/DC converter in an electrical circuit. The check valve can be a fluid diode, such as the Tesla valve, invented by Nikola Tesla 100 years ago, or a vortex diode. These fluid diodes cannot completely stop backflow, but as they have no moving parts, the durability of the pump body including the fluid diode is significantly increased and it can operate almost maintenance-free. Pumps that transport high-temperature melt require an extremely heavy maintenance load compared to pumps that transport ordinary temperature liquids such as water, so the benefits of maintenance-free operation are immeasurable. In this type of AC/DC conversion pump, the piston that generates vibrations in the fluid is in contact with the high-temperature melt, and the rod that moves the piston must be connected to the drive unit through the container of the high-temperature melt. So there is a problem that a shaft seal similar to that of a centrifugal pump must be installed. In addition, the heat of the high-temperature melt may be transmitted to the drive unit through the rod, but the motor in the drive unit generally does not function properly in an environment above 200 degrees Celsius. So there is also the problem of having to cool the motor. The figure on the right is a conceptual diagram of the GOHM-PUMP, which was conceived to solve these issues. In other words, instead of directly vibrating the high-temperature melt, a gas vibration generator isolated from the pump body generates vibrations in the cover gas, and the vibrations are transmitted to the high-temperature melt. On the other hand, since the gas vibration generator is separated from the pump body, it is possible to prevent the heat of the high-temperature melt from affecting the gas vibration generator. With this method, no shaft seal is generated. The above ideas can be summarized in the image of a pump as shown in the figure. Furthermore, if a cooling device for the vibration gas is placed between the pump body and the gas vibration generator, it is possible to strengthen the measures to prevent the heat of high-temperature melt from affecting the gas vibration generator. The figure on the right shows an image of the application of the GOHM-PUMP to a molten salt reactor. The reactor vessel including the core, the heat exchanger and the pump body are inside the containment vessel, which is kept at approximately 500 degrees Celsius. On the other hand, the outside of the containment vessel is insulated by the containment vessel walls and can be kept at below 100 degrees Celsius. As the gas vibration generator is installed outside the containment vessel, it is not directly affected by the heat of the high-temperature melt. The pistons and motors that generate vibrations in the gas are in an environment below 100 degrees Celsius, so no special high-temperature countermeasures are required. The gas vibration generator contains complex moving parts and requires regular inspection and maintenance, but it is free from troublesome problems such as adhesion of high-temperature melt. To summarize the above, centrifugal pumps used in conventional high-temperature melt pumps have the following problems. A. When lubricating oil is used in the shaft seal and bearings, it must be cooled below the flash point. B. As long as the shaft seal exists, it is difficult to completely prevent cover gas leakage from inside the pump. C. Pump maintenance is difficult. In contrast, the GOHM-PUMP does not have shaft seals or bearings, so problems A and B do not occur. In addition, the structure of the pump body is simple and there are no moving parts, so durability is increased and it can be operated almost maintenance-free, which solves the maintenance problem in C. In addition, it has the following excellent features, that is, D. The structure of the pump body is extremely simple, with an extremely small number of parts, allowing for dramatic cost reductions. E. The pump body can be operated almost maintenance-free, allowing for significant reductions in the burden and costs of maintenance. F. There are no general-purpose off-the-shelf centrifugal high-temperature melt pumps, and they must be custom designed according to the pump's operating conditions, such as the physical properties of the high-temperature melt, temperature, and flow rate. In contrast, the GOHM pump has a simple structure for the pump body and gas vibration generator, allowing for easy custom design to accommodate different operating conditions, significantly reducing the pump's development time and development costs. G. The vibration gas cooling device frees the gas vibration generator from the effects of heat from the high-temperature melt inside the pump body, making it possible to create a pump that can handle high-temperature melts of over 1000 degrees Celsius, for example. As an example of how the GOHM pump can be used in the manufacturing process of silicon wafers for semiconductors, let's consider its potential use in the case where it becomes possible to handle high-temperature melts exceeding 1000 degrees Celsius. The most important part of the manufacturing process of silicon wafers for semiconductors is the manufacturing process of single-crystal silicon, as shown in the slide. The most commonly used method of manufacturing single-crystal silicon is called the Czochralski method, in which polycrystalline silicon is placed in a quartz crucible and melted by heating. Next, a seed crystal is immersed in the crucible and then pulled up while slowly rotating to produce an ingot with the same crystal orientation as the seed crystal. This process is performed in a one-time batch production, and both the quartz crucible and the silicon material remaining in the crucible are discarded each time. In batch production, heating, production process, cooling, disposal and reinstallation of crucibles are repeated, but by utilizing GOHM pump, only the production process of silicon wafer ingots can be repeated continuously, dramatically improving productivity. In addition, the crucible itself and the remaining silicon material can be used effectively. Furthermore, the number of times the equipment is heated and cooled can be dramatically reduced, saving energy in the manufacturing process. In any case, the effect of reducing manufacturing costs is overwhelming, and silicon manufacturing, which was previously done by batch processing, can now be produced continuously, which could be a game changer in this field. As explained at the beginning, the GOHM pump is expected to be used in the energy field, such as nuclear fusion reactors, sodium-cooled fast reactors, solar thermal storage power generation, and molten salt reactors, for the time being. However, as shown in the previous slide, in the future, taking advantage of its ability to transport extremely high-temperature molten salt and molten metals exceeding 1000 degrees Celsius, it is expected to be further applied to material processing plants in the material manufacturing industry. Specifically, it is expected to be used in the manufacturing of high added value materials such as silicon single crystals for semiconductors, lithium niobate single crystals used in SAW devices and communication devices such as smartphones, zirconium fluoride glass used as glass fibers for optical communications, and neodymium metal or neodymium iron alloys for high-performance magnets. If these fields are included, the GOHM pump market is expected to reach several $100 billion. As explained above, the GOHM pump is expected to be a game changer in the fields of energy and material processing. Our company, Terry Company Limited, which invented the GOHM pump and filed a patent application, is currently developing the GOHM pump in collaboration with Tohoku University in Japan. In order to proceed with the development of the GOHM pump, a certain amount of research and development funding is required. We ask for your cooperation and support. Thank you for your attention.